Section 5.4, Medians and Altitudes. Well, folks, this is a big one, for a couple of reasons. One is that it's quite long, there's actually a lot of content in it. And another thing is that Section 5.4 is going to be the last section that we cover before your first quiz on Sections 5.1 through 5.4. Also, this section contains some material that has maybe some of the more interesting things that we're going to talk about in this chapter. So let's tune in and first examine a median. So a median of a triangle is going to be, let's see, the fourth special triangle point, or triangle segment that we've talked about. In section 5.1, there was mid-segments, which is similar but not quite the same thing. So there's mid-segments, then there was perpendicular bisectors, then there was angle bisectors. Now we're talking about a median. A median goes from, inside of a triangle, a midpoint, which we're going to assume this purple guy is down here, to the opposite vertex. I've had worse drawings before, it's not too bad. Sure, there we go. Segment with endpoints on a midpoint and opposite vertex in a triangle. So if I really wanted to, I could draw 3 of these things. To there, and another one to there. So spoiler alert, they're all concurrent with a point that's like right there. But before we get ahead of ourselves, let's back up. So a median is interesting because what it does is it splits a triangle into 2 triangles of equal blank slash blank. So let's talk about what those blanks might mean in this case. Let's see what's similar about these 2 triangles. The one on the left here, which I'll call triangle 1, and the one on the right here, which I'll call triangle 2 right now. Well, the area of triangle 2, because that's the most obvious. If I call this segment B, this part right here, and I call the height H, it's very hard to do dashed lines on this. If I call that H, then the area of triangle 1 is 1/2 BH. That's the straight up area formula for a triangle. If I were to do the same thing with the triangle on the left, well, let's take a look for a sec. The triangle on the left had a congruent base, so I guess we would also call that B. As far as the height goes, this one's weird, because if I just forget about this triangle on the right, and I only look at the one on the left here, the height's a weird thing to calculate in this case, because it looks like it's outside of the actual triangle, right? If this is the base, then the height would be, oh man, what a mess. It would be something from this vertex down to the bottom. So I'm going to replicate this down here. I'm going to redraw this triangle. Here's the base, and the height is, interestingly, the height is, if I visualize it, not inside of the triangle. We know it's perpendicular to the base, but it won't actually intersect it. There's the height. So the height of triangle 2 here is actually going to be the same as triangle 1. Here's B, here's my H, which is the same height as it is for the triangle on the right. So wow, it looks like both of these have the same base and the same height, and therefore the same area. So what we could also say is, because this line seems to be cutting the triangle in such a way that the area to the left and to the right are the same, it's also equal mass between the left and the right. That's more of a physics thing that we're going to not really talk about too much, but it's an interesting property nonetheless, that a median will split a triangle into 2 different triangles of equal area and mass. So that becomes big because, as you can imagine, they're all going to meet somewhere, like we talked about. All the medians of a triangle meet at the centroid. Did you know I could actually point with this? I could point. Yay, centroid. So a centroid is a triangle's median's point of concurrency. I'm not going to point anymore, I just want to show that off. Also, it is the triangle's blankety blank blank blank. Okay, so if I look at this down here, it certainly does seem like P is the centroid of this triangle. How do I know that? Well, I see that EA is a median. I see that BF is a median. I see that CD is a median. They all happen to meet at point F. Cool. So if I look at some of the triangles that actually forms, we could kind of prove it in a similar fashion to before. But this purple triangle here, this might take a bit because I have to change colors. This blue triangle here and this red triangle here, if we were to show some properties involving congruence and whatnot, we would see that the blue, purple, and red triangles are actually congruent to each other, which puts P in a weird position that it's actually in the middle of 3. It appears to be the balancing point, or the common vertex, between these 3 congruent triangles. So what we could say, among other things, is that a centroid is the triangle's center of gravity slash mass. Interesting. So, if I gave you a triangle cutout and a piece of paper, hint, because I might do this someday, if I gave you a triangle cutout on a piece of like construction paper or something, and I said balance it on the tip of your pencil. First of all, you probably wouldn't be able to because you'd have to be pretty precise to nail this. But if you were going to do that, what you would probably have to do is find P. You'd have to find the centroid of that triangle, because that would be the center of mass or the center of gravity. In other words, it'd be the balancing point. As you can imagine, this has a lot of applications in things like physics and other realms of science. So anyway, as far as its location, well, as per usual, I'm going to pause this and turn to the Geometer Sketchpad file that you have on your iPads, but I have to go on my computer to get. Once again, if you want to fiddle on your own, this is called 5.4a centroid.gsp. You can find it in the appropriate folder on your backpack, or again, if you're viewing this from the future, in Canvas or something. Also, this one's pretty bare bones, because it seems like there's not a lot going on here. As far as the location of the centroid, well, part of the definition of a median is that it's going to go through the triangle. So if a centroid is where all the medians meet, there's really no way it could be anything other than right inside of the triangle. Regardless if that triangle is obtuse or acute or whatever, no, it's in there, man. So, as far as wrapping things up, it's going to be the case that for the location of the centroid, it will always be inside. Another interesting thing about medians and centroids in general is that a centroid is going to split a median into a ratio of 1 to 2. Very predictably, like E here. By the way, this spells pineapples if you repeat the P and the L. But anyway, E is the centroid here, because we can see that PA and IS and LN are all medians, as indicated by the markings, and their point of concurrency is E. So I guess E is the centroid of this triangle. So it's going to be the case that E splits these into a predictable ratio of lengths, where if I know one thing, then I could figure out a lot of other stuff as a result. So one of the natural questions might be, how do we know which side is twice as big as the other? Is there a certain pattern to it, or like what? Is it random? Can we eyeball it? Well, if I take a closer look at this diagram, I can kind of see that the shorter end always appears to be from the centroid to the midpoint of the sides, like in these three. As opposed to, if I were to look at these red segments now, and say that the distance from the centroid to the vertices always appears to be longer. So it's going to be the case that the two parts of the ratio of 1 to 2, in other words, the longer side that it's split up to be, is going to be the one that is from the centroid to vertex. And the smaller side is going to be the one that is from the centroid to the midpoint of the side. Cool. So, number one, if IE equals 3, then ES is what? Well, this one is cake, or it should be cake, because we could just look at the ratio of 1 to 2 and say, well, I guess that means that ES is twice as big, making it 6. So if EI is 3, then ES must be 6 because of our ratio rule. So, EN is 5, then LN is what? Okay, EN is 5. Whoops, that's not right. EN is 5. Then LN is what? Well, LE is... Sorry, let me back up. LN is not 2.5. LN is not 10. What's happening here is we have to use the whole 1 to 2 ratio thing. We have to use this whole 1 to 2 ratio thing in the same way that we do those splitting a segment into proportions problem that you hate, which is that a ratio of 1 to 2 implies that the first part will be 1/3 of the whole thing, the second part will be 2/3 of the whole thing. So in other words, 5 is 2/3 of what? If you don't like the way that almost word problem is set up, you can just deduce that LE is half of 5, in other words 2.5. So I guess that makes LN equal to their sum, which is 7.5. Ooh, decimals, Mr. Murphy, you jerk. PE. Alright, let's find PE if we know that PA, this whole big guy, is equal to 10. 10. I don't even know where to put the 10. Okay, so the whole thing is equal to 10. So what we should be saying to ourselves is there's a split ratio of 1 to 2. EA is the smaller one. We'll call that x. PE is the bigger one. I don't know what either of them are, but I do know that it's twice as big as x, making it 2x. So if I use the segment addition postulate, what I can say is that x plus 2x equals 10. Okay, let's find x real quick, because that's going to help me find PE. I guess x is equal to 10 over 3, which if I write it as a mixed number, 3 goes into 10 3 times with the remainder 1, that's 3 1/3. Cool. So PE is twice that. So PE is, because if I just plug this x in there, PE is 2 times 3 1/3, which if I double the 3 part gives me 6. If I double the third part gives me 2/3. So I guess PE is 6 2/3. Nice. So, a coordinate plane looking thing here. This one's actually really fun. Whoops, let me just get this centered. Folks, remember to pause this, please, and actually try some of these problems on your own before I actually move forward. But, speaking of moving forward, find the coordinates of P, the midpoint of ST. Use the median UP to find the coordinates of centroid Q. Okay, alright, fine. So P, the midpoint of ST. Well, here's S, here's T. Whoops. There's T, there's S. The midpoint would be, well, let's see. We could just straight up apply the midpoint formula here. This is point P. Okay, so P is going to be x1 plus x2 over 2, comma, y1 plus y2 over 2. That's 16 over 2, which is 8, comma, positive 2 over 2, which is 1. So 8, comma 1 would put me right there, about. Which makes sense, because it's actually on the line. That's great. Notice that each of these grid marks is not a unit of 1, but a unit of 2. So 2, 4, 6, 8 puts me right there. Great. What else we got? Use the median UP to find the coordinates of centroid Q. Okay. So here's UP, because there's P with 8, comma 1. Alright, find the centroid. Shucks. So, this guy is, if I were to look at UP is, if I want to just find the length of this segment, well, the y coordinates are the same, which is great. This is a horizontal line, because that means if I want to find out how long it is, I could just find the difference between the x coordinates. From -1 to 8 is a distance of 9. Awesome. So I can apply this whole 2/3, 1/3 rule relatively easily. We do have to remember, though, which segment is actually longest, because if we forget, it could be either somewhere around there, closer to the vertex, or somewhere over here, closer to the midpoint of the other side. So let's go back. Can I go back? Yeah, I can. So check this out. Remember on this page that we had that the longer side, or the side that corresponds with the 2, is going to be the one that goes from the centroid to the vertex? Well, that means that our centroid is going to be further from the vertex and closer to the midpoint. So I guess it will be somewhere around here. What I would do in order to find out what the answer is to this problem is, first of all, I would acknowledge that the centroid Q has a y-coordinate of 1. That should be obvious, because it's on the horizontal segment with y-coordinates 1. Also, what I should be looking to do is split 9 into thirds. If I split into thirds, then it gives me 3 and... maybe this isn't the best way to do this, sorry. A third of 9 is 3, right? Which means it's going to be either 3 units away from U or 3 units away from P. As it turns out, since it's going to be closer to the midpoint of the other side, it's going to be 3 units away from P. 3 units away from P on the line would be 3 units less than 8, which would be 5. So this guy has coordinates 5, -1. Just to check and make sure this makes sense, this is 3 units here. From -1 to 5, 1 is 6 units. So that checks out. There it is. We have the ratio of 1 to 2. We have the entire length of 9, as we desired. We got the centroid, and that was only part A. Wow. So B is going to be something very similar, to an extent that I'm actually going to go rather quickly here. B asks us to find the coordinates of R, which is the midpoint of TU, and verify that SQ is 2/3 of SR. Okay. So, between U and T, if I do the whole midpoint formula thing, I'll get that these coordinates are, let's see, 5, comma, -1. Great, sure. -1 to 5 would be 6 units, 5 to 11 would be another 6 units. Great, so I guess that does mean that 5 is correct. 1 to -1 is 2 units down. -1 to -3 is 2 units down. Okay, this is kind of like that hop method that we used in Chapter 1 when we were talking about the midpoint. And I'm just doing it here to kind of verify that 5, -1 actually is the midpoint. Great. You could use the formula, check it, whatever. This is a video, so pause and do your work as you see fit. Verify that SQ is equal to SR. Okay, so this is S. Q is in the middle here. Sorry, that's not S. What am I doing? That's R down there. So what I want to do is verify that SQ is 2/3 of SR. Okay. So fortunately, this also works out really, really nicely in that this line is vertical. Great. So from S to Q is, notice how these all have the same x-coordinate, but from S to Q is a distance of, let me pick a color to write in here, 4. I really wish I could zoom in, but I can't, I'm afraid. 4. From Q to R is a distance of 2. And then this entire thing, from S to R, is a distance of 6. So that seems to check out also. SQ is 6. Sorry, not SQ. SQ is 4. Ugh. SR. Oh my gosh. 4. SR is 6. And 4 is 2/3 of 6. So I guess that checks out too. Okay, so all this stuff checks out. Wow, what an exhausting lesson. You know, we're only about halfway through. So I'm going to pause this video and let it end here. Stay tuned for 5-4 Part B coming up.